Energy can come in different forms. Like last week, we talked about energy in the form of kinetic energy. And this week, we are going to be looking at potential energy. And potential energy can be branched into many other kinds of energy, such as gravitational or, say, elastic. Okay? And in this video, I'm going to be looking at gravitational potential energy. So let's look at potential energy in general. Potential energy of an object is known as the energy due to its position or shape. Position being a position in a field or position compared to another object, or its shape. For example, elastic potential energy, that is based on the shape of the solid that we are going to stretch or compress, which I'm going to talk about in another video. So gravitational potential energy is the energy due to the object's position, but position where? In a gravitational field. Similarly, with electric potential energy, it will be the energy due to a charge due to its position in an electric field. So gravitational field is the effective influence, the area of effective influence of gravity that a object. An important thing to notice is that gravitational potential energy, as I said before, is basically the ability to do work, and it in this case is the ability to do work in a gravitational field. So if it has energy in the gravitational field, then it has the ability to do work in that gravitational field. So it is like a stored energy in that gravitational field. And usually it's a position away from the center of a mass, such as I am standing well above the center of the Earth, where supposedly the entire mass of the Earth appears to act. Okay, so it is the ability to do work in the gravitational field, and this energy of a particular object it depends on the three things. It depends on its mass, it depends on the height, or say the position in the gravitational field, which we commonly look at as height, and the gravitational field strength, how strong the gravitational field is. So we think about it. Think about gravitational potential energy as the ability to do work. If you have greater mass, you're more likely to have greater energy to be able to do things with greater amount of energy. If you look at kinetic energy, similarly, the greater the mass, the greater the kinetic energy, the greater stored energy that you're throwing this huge mass to. And similarly with the height. The higher you are above the center of mass of an object that you are considering as your gravitational field producer, then you're going to have a greater amount of gravitational potential energy, because you're going to be able to harness that position to be able to do work in that field. You have that great amount of height that you can exploit, through which you can transform this energy to other forms of energy. And gravitational field strength. So the stronger this object is able to be in this gravitational field, in the sense that it can be pulled down stronger, and that can give us greater amount of energy. Okay. So when we look at gravitational potential energy, we look at two kinds of gravitational potential energy. Relative gravitational potential energy, that we commonly say, but we don't really understand that it is actually relative. I'll explain what I mean. Gravitational potential energy relative to a position is equal to the mass multiplied by the gravitational field strength multiplied by the height relative to that position. So usually in mechanics questions, we're going to be looking at heights relative to the ground. Okay? So the gravitational potential energy of an object is equal to the mass multiplied by the gravitational field strength multiplied by the height relative to a reference, like we usually use the ground. Okay, so if we were to find the gravitational potential energy, so more commonly we will be asked to find the gravitational potential energy of an object relative to the ground. So it's usually the ground that we're going to use as our reference point. So H is the distance from the ground. As we said, it's 5 meters indicated in the diagram. And the gravitational potential energy of this object, therefore, relative to the ground, is equal to 3 kilograms multiplied by g, which is 9.8, multiplied by 5 meters. And this gravitational potential energy is equal to 147 joules. But more commonly, we look at GPE in a sense that we can do work from it. So therefore, if we're able to harness this GPE, then more likely than not, we are going to look at the change in GPE that might cause another change in, say, kinetic energy. So that change in GPE is converted into a kinetic energy or, say, elastic potential energy. So we therefore look at gravitational potential energy in a more broader sense, in that the change in GPE is related to its change in height. So if I were to lift this object through a certain distance, through a certain height, I would change its gravitational potential energy. And the amount of height in which I change it through is proportional to the increase in the gravitational potential energy, which we can therefore derive in this delta GP is equal to mg times delta h. Okay? Where GPE is directly proportional to the change in GPE is directly proportional to the change in h. Now find the change in the gravitational potential energy when an object of mass 5 kilograms is raised through 4 meters. As we know, the change in gravitational potential energy is equal to mass multiplied by gravitational field strength multiplied by the change in height. And that is equal to 5 multiplied by 9.8 newtons per kilogram multiplied by 4. Gives us the answer. Brilliant. But, for example, this object is falling to the ground, and it is initially raised 2 meters above the ground, and it falls to the ground, and we're asked to find the change in gravitational potential energy, and that is equal to mg delta h. We can plug in all the values, and you can get 98 joules. So let's discuss a bit. So let's look at the situation that we talked about earlier. So if this object was to fall to the ground, it's going to hit the ground hard. It's going to gain kinetic energy, and then it's going to hit the ground hard. But where does this change in gravitational potential energy go to? So we know that, of course, it has to go to kinetic energy, right? But let's look at it in a collision way, as I've talked about in the past. That what if this was an elastic collision and there was no air resistance? Then, of course, the ball would have to hit the ground, and it's going to bounce right up to the same height and then continue hitting and going back to the same height, up and down, up and down, up and down again. But in real life situations, there is an atmosphere. We have air. So we are going to lose kinetic energy. We're going to lose the gravitational potential energy as soon as the ball starts moving. Okay, so it's going to lose energy. And in the next video, I'm going to talk about work energy, the work and energy principle, in that this energy can be converted into this energy, and we can use mathematical models to model this, basically.